Hi, everyone. I'm Byron Wasti. I'm going to be talking about the performance pitfalls of async function pointers in Rust and why they might not matter. A little bit about myself. So I've been programming with Rust for 7+ years now, 4+ of them professionally. I've focused on building robust, high-performance, low-latency systems. I'm also the developer of the new open source load testing framework for Rust called Bolter, which you can find on GitHub. Founder of Bolter Load Testing, which is consultancy based around this load testing framework. And for this talk, I'm going to be using that load testing framework as the motivation for kind of why I did this research. And really specifically, when building a load testing framework, one of the kind of key bits of functionality you need is the ability to run some user-provided function repeatedly and possibly in parallel. So you can imagine some load test framework on the left and some user code on the right. The load test framework might provide some load test function, which takes in some arbitrary user function and just runs that arbitrary user function on a loop to kind of provide that load. And the user, on the other hand, on the right side, would just call that functionality by importing that framework and then calling load test on their provided function. In the synchronous world of Rust, this is very simple and very straightforward. So using function pointers, you can kind of have this load test function, this load test framework, work on any function that provides that same signature. So any function that doesn't take in any arguments and doesn't return any value, you can pass into this load test function. And you can run that function, that user-provided function, in multiple threads. You can run it repeatedly. You can kind of do whatever you want. You can also send that function to other machines. It's really just a pointer. And so you can see we're calling this load test with myfunc A, myfunc B, myfunc C. All of it's the same, and all of it's very simple to work with. Now, Rust provides async functions. And for IO-bound tasks, async really promises a lot of performance benefits. So you can imagine for load testing an HTTP server, your load test will really consist of mostly HTTP requests. And so you want to use async to kind of leverage the async functionality in Rust to make it way higher performance so that you can provide way more load to your service under test. And you might imagine that in order to do this, all you need to do is take your synchronous load test framework and add some async keywords to everything. That's how you turn a synchronous function into an asynchronous function. So you might imagine, okay, to turn a synchronous function pointer into an asynchronous function pointer, you can just provide an async keyword. Unfortunately, this is not the case, and so this doesn't work. The compiler will complain and say async func doesn't really make any sense in this context. And I'm going to dive into why this is the case just really quickly and briefly. So async functions in Rust, what they actually do is they desugar into normal functions which return impl future. So if you're unfamiliar with the impl trait in Rust, what it does, it tells the compiler to auto-generate some opaque type for the return value of some function. And this is extremely useful for things like iterators or functions that return iterators. And especially, it was added to the language specifically to support async functions. And what it really does, it's kind of a way of saying, like, this function returns something, but you don't really necessarily want to name what that something is or kind of describe what that something is. You just want to say that something implements some interface. So for async functions, it's something that implements the future trait. And what this kind of means is that this opaque type is different for every single async function. So even though foo and bar have the exact same function signature, they have async, they don't take in any arguments, and they return an I32, you can't actually treat them as the same thing. So you can't put them in an array together. And to not go too deep into the details, I'm just going to briefly describe kind of what the compiler is doing to generate that opaque type. So when the compiler generates that impl future type, what it's actually doing is it's generating some struct which implements a state machine which runs the functionality in that async function. And so that struct contains, the various function pointers to the various kind of subparts of your function, as well as the variables that are carried across await points. So essentially, it's not just kind of that I32 that's being returned from that function. It's this whole struct which implements future as a trait, and that struct runs kind of some state machine. And so when you kind of think about async functions in this way, it becomes very clear why you can't treat foo and bar identically, because their opaque type that they're returning is dependent on what the body of that function is, which is, a bit of asymmetry to synchronous functions. Synchronous functions, you can kind of just look at what the signature is and know everything you need to know about them. Async functions, their signature is kind of dependent on what the body contains. So that's really the key part here, is that async functions, even with the same signature, are actually totally different. The common workaround is this concept of a type erased async function pointer, and it's to use a box pin. So box pin is a bit of functionality that puts that trait, or, it's a bit of functionality to take that, auto-generated future that the compiler generates and put it on the heap and allow you to treat it as a trait object. So a trait object on the heap, you can then treat identically. So here, rather than kind of allowing the compiler to desugar, we're running foo and bar ourselves, manually desugaring it into a pin box trait, future trait object. And I'm not going to go into what pin is. There's a lot of kind of tutorials on kind of what it is. It's a bit complicated. It's really just a marker type. But essentially what this means is that you're now allowed to kind of treat foo and bar identically again. So foo and bar, you can kind of put them in an array together. They're the same thing. And this is kind of a very common workaround. It's always the suggested thing. But there are some performance implications. And oftentimes, if you ask online or you read kind of various tutorials, it'll say, yeah, you can just use box pin. There's some performance overhead, but no one really talks about like what that performance overhead is. And so I was using box pin for the load testing, just kind of get it off the ground. And I wanted to know, okay, like what are the performance implications? In order to measure performance characteristics, I set up a very simple kind of benchmarking suite. So here is what the code looks like for a synchronous function. Really, it just, it mocks some load test functionality, which takes in some function pointer, and then calls that function pointer 250 million times. And I tried to kind of use black box in a bunch of different places. Black box is just a compiler hint to tell the compiler to not optimize things away. Otherwise, the compiler just like optimizes everything away and you don't really get to benchmark anything at all. When running these benchmarks, I did it kind of on a set of different things. So first I did a function pointer, which ran in about 430 milliseconds. I then did a box function pointer. So you can imagine that function pointer, but now it's just on the heap. So there's a little bit of extra dereference. So it takes a little bit more time. It's at 537 milliseconds. Then I did just an async function. So not an async function pointer, because those aren't really a thing, but just a normal async function. You can imagine that's slightly faster than a function pointer just because there's no dereferencing involved. And then finally, I did the boxed async function, which, as you can see, is at around 5 seconds of runtime. And this is about an order of magnitude slower than all the other options, which I found to be a little surprising. Everyone says, hey, box, pin has some performance overhead, but they don't really say, hey, box pin, will have a 10x performance overhead. That's kind of a pretty surprising result in my mind. So what's probably going on? Box async function pointer, box async functions, order of magnitude slower than kind of box functions, order of magnitude slower than just normal async functions. What's probably going on is that, that heap allocation includes the state machine struct the compiler is generating. So normal function pointers, that's just a pointer on the heap. But for an async function, it's just this whole opaque state machine struct. There's a lot more data that needs to be allocated and initialized, and that is likely what's explaining that kind of performance consequence. I didn't dig too much into it. Kind of reading the compiler output with Godball is a little tricky with async functionality. I'm not very good at it, but I'm kind of assuming that's probably what's going on. But really what I focused on is looking at what are the alternatives, kind of what are the other options that we have to kind of get this sort of async function pointer like behavior, but without the performance overhead of a boxed pin. So the first alternative isn't so much of an alternative as more as just kind of a way to reframe the problem. And that is by pushing that boxed pin to the edge. So it's kind of making use of generics such that your boxed pin call is only done very rarely or once. So here, what's different about this load test function is now it's generic over the user provided function. So the user provides some async function foo, provides some async function bar, and load test is now generic over that foo and over that bar. And instead of box pinning foo and box pinning bar and then passing that into load test, we now box pin load test entirely. And so you can imagine is that before our framework had some load test functionality that took in some wrapped up user provided function that we could treat all the same way. Now we're saying, okay, we're going to make load test generic. We're going to monomorphize it over every kind of user provided function. And then we're going to wrap all of that up and then treat all of those kind of load test blobs the same way. So you can kind of put those in an array. You can kind of do all the same things that we want to do. We can treat them identically again. And this has major space considerations just because the compiler is now creating a new load test function for every single user provided function. So the binary will take up a lot more space. It's monomorphized over every user provided function. But the idea is that this should have way better performance characteristics. When measuring performance, we kind of found this to be the case. In fact, it's found it to be faster than async functions, which doesn't really make any sense. It shouldn't be, is kind of my takeaway. Realistically, I think I'm missing some black box compiler hint to tell it to not optimize something away. And so there's probably some additional optimization the compiler is doing under the hood in this benchmark. But in any case, I think it's clear to see that the generic async box, kind of pushing that box pin to the edge, is way faster than just repeatedly calling box pin. And this, should make sense. Is not a very surprising result, other than the fact that it's slightly faster than an async function. But I think that's just kind of an issue with the benchmark. The second alternative I kind of investigated is using an enum. So rather than having the load test take in kind of any generic user function, it'll take in some enum func here, which is just an enum over the different functions they might run. And then that enum has some implementation on it run, which will shell out to the actual async function calls. And so you can see here, func is either foo or bar. And when you call run on it, it'll either call the foo async function or the bar async function. And so there's no heap allocation, there's no indirection. It's all kind of very, very direct. This has the major downside that you need to know all of your async functions at the start. So you can't kind of provide it for any user function. You have to kind of know them all ahead of time. But this can still be very useful if you kind of know what you're doing, or if you know all of your async functions and you're not writing a load test framework. And so this is kind of a nice other alternative. When looking at the performance characteristics of this kind of async enum dispatch system, it's slightly slower than an async function call. This makes sense. You're kind of going through that enum match. You're doing a little bit more work. And so, it's a pretty negligible overhead. It's kind of similar overhead to just boxing a function pointer. And so I think, this is kind of a very reasonable alternative, and the performance characteristics make sense. The third alternative I want to talk about, and I didn't benchmark it because it's rather tricky to benchmark, and really I'm just want to talk about it because I think it's a very kind of cool trick, and I found it by just browsing various code. So this is used by the Tower Rust framework for the rate limiting functionality. And what it is it's taking a future and just resetting it. And so you can imagine for some load test framework, you're taking some user function, you want to run it repeatedly. If you're taking a box pin asynchronous user function, you might have to allocate the state machine structs onto the heap, run the function, then deallocate it, and then allocate another one, run the function, deallocate it, and you have to kind of do that repeatedly. And so there's major performance implications of constantly allocating and deallocating that state machine. If you were able to just reset it and say, hey, like the state machine, we're only going to allocate it once, and then when we're done running that function, we're going to reset it to its kind of initial values. Then you're not kind of dealing with the overhead of allocating and deallocating repeatedly. Unfortunately, I couldn't find a generic way to implement this over like any async function. In theory, this seems like it should be somewhat possible, but I couldn't find one. So I wasn't able to benchmark it or kind of measure it. I think this was just kind of an interesting alternative to keep in mind. And then finally, I want to talk about, putting this research, kind of implementing it in practice. So I converted Balter to using generics. So kind of using that first alternative I talked about, which is pushing that box pin to the edge. And I saw no performance difference whatsoever, which I think is kind of one of the consequences of doing, a micro benchmark of a very niche bit of functionality. Which is that it can make it seem like something is a big deal when it's really not. And that's because, function calls are ridiculously fast. They're probably one of the most optimized things that you can imagine a language has. We call functions all the time. And so a 10x slowdown over a function call is still really, really fast. And so I think this was, kind of just a thing that I need to just realize is like, oh, actually, this doesn't really make a difference whatsoever. Balter was able to kind of, just push out the same amount of load no matter what. And I just want to kind of note that there is a storage RFC for Rust, which someone commented when I posted about this research online, and they just said, hey, the storage RFC, it'll add kind of new options in the future. So alternatives to box pin that still provide that kind of type erased async function pointer behavior. And that's all I have. So thank you so much for listening. Once again, I'm Byron Wasti. You can reach out to me, P99 at byronwasti.com. Also, here's my website and my GitHub. And thank you for listening.